Okay, welcome to Chapter 4 and matrices. This first lecture actually covers both 4.1 and 4.2. We will do part of the problems from both, so it won't be like two full new assignments. All right, let's take a look at what our goals, standards, objectives are. We want to be able to use a matrix to store data, and we want to graph figures described by these matrices. So, a couple things we need to do is to learn about what a matrix is. A matrix is singular, matrices is plural. You can see it's a rectangular array of numbers written with brackets. You represent a matrix with a capital letter and classify it by its dimensions. The number of horizontal rows and vertical columns determine the dimensions of the matrix. So if we're talking about what it's going to look like, then we will say we have a matrix that is maybe 2 by 3, and we use squared off brackets, and a 2 by 3 matrix would have 2 rows with 3 columns, and in each of those spots we would be placing a element, a number that represents something. Now, it can be all kinds of sizes, as we're going to see momentarily. So if we look at the possibility of matrices, here is that example where it says we like to call them a capital letter. So in this case, we have our capital letter A. We do have 2 rows and 3 columns, and we have numbers in each of those positions. So matrix A, we like to say, is a 2 by 3 matrix. It's always row by column when you're identifying the size of your matrix. So if we look at these and we want the dimensions of each, look at them. We don't care what's in them, we just want to know the dimensions. It says A, 2, and 3, so I really just say number 1. So on number 1 here, our dimensions, looking at it, should be a 3 by 3. Look at number 2. Again, remember rows and columns, so it's a 1 by 3. And then rows, it's a 4 by 1. And then if you have to write a 3 by 2, you should be able to write your little squared off brackets, maybe not make the brackets so large. And then 3 rows and 2 columns should look, even if I put all the same combinations of numbers in, 3 rows, 2 columns, yours should be similar. Write the dimensions of this matrix. If we had our clickers, but we don't, so right now we would say we have A, B, C, or D. If you answered it correctly, the answer should be A. Now, each number in a matrix is the matrix's element. You can identify a matrix element by its position within the matrix. Use a lowercase letter with subscripts. The subscripts represent the element's row number and column number. So identifying the element A sub 1, 3, A 13, some people like to say, in a matrix A below, we'd be looking at the first row, third column number. So first row, third column number. Everybody should be identifying A sub 1, 3 as the element 3. So if we now look at this one matrix called A, and we want these different combinations, so start looking at what elements would go where, and we'll do a quick test to see if you're accurate. So if we want to identify the matrix elements A sub 1, 1, you better be looking at first row, first column. That element would be 17. A sub 2, 1, second row, first column, that would be 10.4. What is the element in A sub 1, 2? That would be first row, second column. You better be looking at 24. And lastly, the first row, third column would be that element 3 that we identified previously. Three, 3 in this element, again, would it be choice A, B, C, or D? The correct answer is D. Now, what you have to understand is matrices hold data. It can be almost any kind of data. In this case, we have statistical data. Successful businesses must track great amounts of data in order to plan the best use of their resources. They use matrices to organize and compare statistical data. Now, if you look at this data chart, it is based on production and consumption. It's energy. Write a matrix to represent the data below. Estimate the values from the graph. So you don't really have pure numbers here, so you are going to be estimating, and we'll just do a couple to try it. But it does say let each row represent a country. So you know your rows represent your countries. So let's just think right now China, Russia, and the United States. And each column represents production or consumption. So right now we'll be thinking production, consumption. So when we make our matrix, we could fill in the numbers accordingly. So looking at the China's production and consumption, you look, okay, they're a little over 30, not quite 35, so maybe one's 33 and one's 34. So China would be 33 for production, which was red, and 34 for consumption, or maybe even 33.5, but they don't look like they're exactly the same. For Russia, look at that, a little over 40, so maybe 41, and the other one maybe 26. We're just eyeballing, but we're getting our data off the chart. And last one, United States, our production of energy is maybe 72, with our consumption being way more, up near 95. And so that's where we would get our information data to put in a table. So you can take statistical data, graphs, and chart the data as well in a matrix. So how could you modify your matrix to include data from other countries? So if you go back just for a second and look at where the things were, we want to modify and add other countries. So what would we have to do to that? And again, look at your choices. Would you choose A, B, C, or D? And if you remember, our countries were in our rows, so we could add a new row for each additional country, which is choice B. Here's another one. From the 2000 Olympics in Sydney, you have the scores and all the girls who were on the Olympic gymnastic team. And so we could ask you, in this case, just looking at the data, it's sort of a matrix in itself. It says you can write a matrix to represent the information, but if we did, which element represents Kristen Maloney's score on the vault? If you would leave the data exactly as it is here, then you could say we're in the third row to be at Kristen, and then the vault is in the second column, so the A sub 32, if you still want to name it A, that element would be her vault score. You know, so basically what we said was this is our matrix, if we were going to take that data and put it right into matrix form. All right, section 1's done, just how to store data. So section 2, we want to be able to now add, subtract, and find scalar multiples of matrices. This isn't bad, it goes quick, and it's based on your addition and subtraction that you learned way back in elementary school. So let's try a few. You can perform matrix addition on matrices that have the same dimensions. So that's key. You must have the same dimensions in order to add. And then it says by adding the corresponding elements. So there's another key piece. Corresponding means first row, first column with first row, first column in the others. So in this case, we were going to get, we're going to get a new matrix is our answer, and that matrix will be an identical size because they have to be same dimensions. So we're going to get a 2 by 3, and we add corresponding parts. So we're adding the first row with the first row, first column with the first row, first column, first row, second column with the first row, second column, etc. And as we go right on through, then second row, second row. So the sum of the numbers is because we added each corresponding part from the same dimensioned matrix. So you can try this one for number 2, and we will check it in class. There are 2 special types of matrices. The first one, called the additive identity matrix, for the set of all matrices, m by n, is the zero matrix. So this additive identity matrix, the zero matrix, has zeros in every single slot. And so when we would add the additive identity to any matrix, we should get back what we started with. So in this case, we got back to our original 1, 2, 5, -7 matrix, a nice 2 by 2. The opposite, or additive identity, is a little different. So we sometimes call it the opposite, sometimes we call it the additive identity. 2 words for the same thing. We're up here again, remember it was called additive identity. Additive inverse, so they are slightly different. The opposite, or additive inverse, is when you add 2 matrices that are opposites in each particular corresponding part. So again, if we add matrices, they have to be the same dimensions. They are. This is a 2 by 2. This is a 2 by 2. But notice, in each corresponding part, we have opposite values. So what's going to happen here? We're going to get that matrix that represents that zero matrix. It is also a 2 by 2, so we get the same size we started with. But we end up with the opposite, or additive inverse. And notice they say, if I started out with matrix A, its opposite or inverse matrix is said to be negative A. So just a little symbol, some new symbols to keep track of as we work with matrices. All right. Now, if 2 matrices A and B have the same dimensions, then it says you should be able to subtract them. And subtracting, as we learned with regular numbers, is the same as adding the opposite. So you could subtract if you like, if you are comfortable with adding different styles of numbers as the opposite, or you could subtract as normal. So you have 2 choices, subtraction as normal or adding the opposite. On this first one, let's go ahead and subtract as normal and see what we get, knowing that we have 2 dimensions, 2 matrices with the same dimensions. So we have a 2 by 3 to start with. Subtracted from a 2 by 3, we had better get a 2 by 3. So here we go. First row, first column, that's 3 take away 1, or 2. Then we go across, filling in across, 2 take away 4, 4 minus 3. Now we go to the second row, -1 subtract a -2. Be careful, because that would be -1 plus 2. Then 4 subtract 2, and then 0 subtract 4. So in the end, you still have a 2 by 3, but that matrix represents the subtraction, or the difference of those 2 matrices. Now, if you subtracted on this first one, try doing add the opposite when you do this second one. Okay? So add the opposite. So be careful when you add, and we'll check that one in class. See what you get. Moving forward, there is something called scalar multiplication, and you actually learned a little bit about it in elementary school when you were doing your basic facts. Scalar multiplication. The scalar k and a matrix A are multiplied by making each element in the matrix A times K, that matrix A, K times larger. What that means is, look at this combination. If I asked you to add these four matrices, you should notice there's a pattern. You say, well, wait a minute. Those first three are identical. So when you had repetitive things and you were adding, that's when you started learning your multiplication tables. So if I could write that in an easier way, I know I have three of those and three of the exact same thing, we would write it with the 3 out front. That 3 is called the scalar. That's the k we were referring to. So we could do a much easier problem by doing 3 sets of this first matrix plus that one matrix that was different. So the very next thing would be to do triple each of the numbers in that first matrix. So 3 times 2 is 6, 3 times 0 is 0, 3 times -6 is -18, and 3 times 4 is 12. That gives you a new matrix, and that matrix is a 2 by 2. It can be added to that 8, 6, 1, -3 matrix, which is also a 2 by 2, for a final total of 14, 6, -17, and 9 in a, again, 2 by 2. So that's scalar multiplication. Anytime you have repeated addition of the same exact matrix, you can quickly use your multiplication, scalar multiplication. Now let me caution you. Scalar multiplication is not how we do all multiplication with matrices. So there will be something different. Today we're focusing on adding and subtracting and this one type of multiplication called scalar. All right. Next, a matrix equation is an equation in which the variable is a matrix. So in this situation, you have to be thinking, hey, we're subtracting. And if I'm subtracting, the only way we can subtract is if we have like dimensions. So we know right now that these are 2 by 2s. So we know we're looking for another 2 by 2 to go here. And I'm just copying as my work or setup on my paper here. So I'm copying what I know. And in my mind, I've set up the missing piece. And there's 4 slots. And I will do them one at a time because we already know how to subtract. So your brain is saying, what number subtract 1 has to equal 0? Because these are all the elements that are in the first row, first column. So if you go back, I'm saying this number minus this number has to equal this number. So something take away 1 equals 0. What is that number? Well, it has to be a 1. All right? The next row, or same row, different element, upper right-hand corner. So I now know something take away 1 has to equal 1. Well, let's see. Most people would say that's a 2. Next number, and you don't have to do this in color, it's just for the emphasis here. The next slots down here, I have some number, and when I subtract 3, I'm going to get the answer of 8. So most of you know that that would be an 11. Last one. What number subtract 2 equals 9? And again, we're looking at an 11. So when we finish, we know the missing piece, or the X matrix, is actually equal to this 2 by 2, which was 1, 2, 11, 11. Now, to determine whether matrices are equal, that's the key piece here. So that's what our value is. We're trying to determine whether things are equal. Look at each pair of elements in the same position. Matrices must be the same dimensions. So to determine whether they're equal, look at each pair of elements in the same position. So that would be the corresponding elements. Now, in this example, it says both A and B are 2 by 2s, and we can see that. And their corresponding elements are equal. So if you looked at this, you were supposed to be comparing the first row, first column. Over here is the number negative 75 to over here, the fraction negative 3/4. In order to do that, you just have to say, okay, they're not the same exact number. One's a decimal, obviously, and one's a fraction. But do they have the same value? That's the key. So if they do, then you're good. All right? So then I would say, okay, what about the first row, second column position? Is 1/5 the same as 0.2? Again, one's a fraction, one's a decimal. But they are, so yes. And then the 1/2 compared to the 0.5, we know that one's pretty easily. And then lastly, the -2 and the -2 are the only ones that are exactly alike, so that was easy. Okay, so they are equivalent because they're the exact same size and they have equal values in each position. So, knowing that, what about these? Are they equivalent matrices? So again, take your brain, if you have to, calculate it if the numbers get too big, and start comparing. Are we good in the first slot? Are we good in the second slot? And are we good in the third slot? If your answer is yes, then those two should be. Assuming you already looked at the size. So maybe sometimes it's easy to look at the size first. So if right now you're saying, well, 4 is 8 over 2, 6 is 18 over 3, and 8 is 16 over 2, I'll go back and ask, did you ever compare x to y in terms of their size? Because the first thing we said over here, that the matrices are equal and the dimensions are the same. So we have a 3 by 1 sitting here, and over here we have a 1 by 3. So right away, they are not equal because they are not the same size. So let's go and do this one. Size first this time, because if that's the easier item, we have a 2 by 2 here. Over here, look at it, we have another 2 by 2. So we can't say they're equal just because their dimensions are the same. So now we'll start comparing their elements. So first row, first column with first row, first column. Looks good. First row, second column with first row, second column. Also looks good. Second row, first column with second row, first column. Second row, second column with second row, second column. So now we can say most definitely, yes, these are equivalent. This up here again was the big no. Okay? So use your eyeballs. You don't have to color things in like I did, but that's what you should be looking at to make your comparisons. Equal matrices. Okay, we have another equation we can solve. This one is addition. It would be solved the same way, but you got to look and say, all right, it's a 2 by 2 I'm looking for, and I have 4 slots. So I need 4 numbers in that 2 by 2, but we're also looking at addition in this case. So something plus a -1 equals 10. Something plus 0 equals 7. Something plus 2 equals -4. And something plus 5 equals -4. So you just do your arithmetic on each element as you go and make sure you're following, is it addition or is it subtraction. Next, we'll pick one of these. We don't have to do them all because they're all done very similarly, but it says find unknown matrix elements. If you look in each one of these,
those students that were taking plan tests this morning that did not have special accommodations are now completed with their exams, should be heading back to class. Thank you.
So if we take any one of them, you first want to look and say, okay, they all say they're equal. It's because their dimensions are the same. You know, up in number 1, we have 2 by 2s. In number 2, we have 2 by 1s. In number 3, we have 2 by 2s. And in number 4, we have 2 by 2s also. Okay? Let's just take, for our purposes here, let's take this number 4 and work through it. This is how you would solve it when you have unknown pieces. So if you know 2m minus n has to equal 15, you basically have an equation. So we'll go to the next element. Well, the next element, first row, second column, says negative 3 has to equal m plus n. So again, still you're looking at, oh, that's a little different. And what we need next is 8 equals 8. So we really have nothing to do there. And then negative 4m plus 2n has to equal negative 30. Okay. Now, obviously, there's several things you can do. You could do trial and error, I guess is what I wanted to say. You could try to make them equivalent. You could pick choices that go in to the equation, meaning like if you take the easiest one here, if 4 plus, taking this equation, if you know, make it negative 4 plus 1 is negative 3, will that negative 4 and 1 work here? And you could play around with the numbers. There is also something called a system of equations that would make that work nicely, but we haven't done systems yet. So that's why I started with number 4, because if you pick that one out, you might get a little frustrated. So we'll leave that one alone to start with now, but let's look at, maybe back up here at number 1. If I'm looking at this 2 by 2, I can see that 2x minus 5 has to equal 25. Well, if you remember, that's a one variable equation. We could solve that by moving the 5 to the other side. Oops, by adding 5. When we add 5, we get 30. So we now have x equals 15. If x is 15, we can use that to finish the matrix. When we finish, obviously, we want a completed matrix. So right now, if x is 15, go back up. 2 times x would be 30. 30 take away 5 is 25. So we know that's a 25. We know that's a 4. We already knew that was a 3. We have an x value of 15, but this next part needs a y, so we'd say the equation 3y plus 12 has to equal, according to this, y plus 18. And you'd solve that equation by first bringing the y's over. That would give us 2y. Taking the 12 to the other side, that would give us a 6. Y equals 3. If y equals 3, then do the math. 3 times 3, up here on this statement, 3 times 3 is 9. 9 plus 12 is 21. So your matrix would be 25, 4, 3, and 21. And so that's how you would solve those. Again, remember, number 4 is slightly special. We would use probably what we call systems, which we haven't talked about yet, to solve it. So you should be able to do the other two, though, looking at them, because they are all single variables. This one is 2 variables, which makes it a little tougher. All right. Last but not least, here, there's some more subtraction practice if you'd like it. More addition practice. Again, a different subtraction. So we're going to be working on 2 sets of problems from those sections. And if you didn't catch them right there, they'll be on MBC. And so just work through how you store data in a matrix and also how you add, subtract, and use matrix multiplication is what we're dealing with in these 2 sections.